Right, this lecture is about section 4.3 out of the book, which is additional simplex algorithms. This is a very short and quick section. So the idea here is that the simplex algorithm had a couple of preconditions on it. For the simplex algorithm to work, you have to start at a feasible point and a basic solution. And that solution is, in most cases, a non-optimal solution. So it then hops from corner to corner around the feasible region in a smart way until you reach the optimal solution. What happens though if you don't start at a feasible point? So if you think of your feasible region as something that doesn't include the origin, for example, generally with the simplex algorithm, the easiest way to do it is to start at the origin. So what if that is not a feasible point? When you have this, you can make use of something called the dual LP, or the dual simplex actually. The dual simplex algorithm is for when you start with something that is better than optimal, but is infeasible. So it's something where the result of your objective function is more than the optimal value, or better than the optimal value, but the problem is that you're in an infeasible area. The idea here is that we just saw that you have this primal and the dual. And they have the same optimum solution. If you are in a situation where you have your value being better than optimal, we can flip over to the dual, solve the dual using the simplex algorithm, and it brings you back to the optimal solution. It's essentially just using the simplex algorithm on the dual. A couple of conditions for it to work. The objective function has to have at least one positive coefficient. That's where you're dealing with a maximization problem, and all constraints have to be less than or equal to 0. So it's basically like the simplex algorithm. Here are these how you choose, but let's see by an example how it works. So if we have this simplex tableau, the rule says that you look on your right-hand side and you find something that's negative. Now, when there's something that's negative, that's going to give you that it's infeasible. Those are the infeasible ones. So you find something that's negative, and in fact, you take the biggest negative one on there. Now what you're going to do is you're going to ignore your basic variables. You're only going to look at your non-basic variables. And remember how last time we said use a ratio? You do the same thing here. You're going to use the ratio to figure out which variable to take in and out. The row that you choose, the one with the largest negative number, that is the basic variable that is leaving your basis. Now you have to find the non-basic variable to enter your basis. So for this, you take your z value and divide by your matrix value in the row. Do it for all of the non-basic variables where your matrix value is positive or is negative. So for x1, you have -1 divided by -1 gives you a 1. For x2, you have -8 divided by -4 gives you a value of 2. You take the absolute value of it, I should say. You take the absolute value. For x3, you have a positive number in there. That means you ignore it. So you only look at the negative numbers in the matrix. Take the ratios. So remember when you're doing the simplex, you took the ratio of the right-hand side to the number in the matrix. Here you take the ratio of the top number to the number in the matrix. Find the smallest one. It'll be that one. And that is your pivot point. Now you just do the pivot the same way as you do for the regular simplex. What it's going to do is it's going to change your solutions to tend to give you positive numbers on the solution. So the book also talks about something called a generalized simplex algorithm. Now, in the book, in the book, he talks about how this is something he developed. I'd kind of question that because it's almost the exact same as something called the primal dual algorithm for simplex methods. I'm not gonna bother going into it very far, but basically the idea is that this dual method that you just saw, you do that until you can't do it anymore. Then when that's done, you apply your regular simplex method to what's left over. So it's very straightforward, very, using the dual method followed by the primal simplex method. And the idea is that you have a non-optimal and infeasible point. So you have an infeasible point that the dual doesn't really work for, but you can use the dual simplex method to get you into the feasible region, and then the primal simplex method to get you the optimal point. There are some examples in the book and some exercises for it that kind of go through it. But if you know the dual method and the primal method, it's just doing one after the other. That's a very short section on using the dual method. I am going to talk more about the dual method in more general at a later point, just about the dual LP, and we will probably at that time get into a bit more about why this dual method works.